It's very variable from country to country. It depends on their capabilities. So most of the models we use in science are not really very useful for this. And it's one of the things I was saying is you kind of realise that, so the process of coming up with these accounting methods, it's not like if you sat down as a scientist and thought about the best method, probably wouldn't necessarily be a model anyway for doing country-based accounting, but I've been out and measured trees, so I do know a bit about measuring trees and things. The methods develop in a kind of sort of pragmatic way of what you can actually get countries to agree on doing. So they're very specific and odd-sounding rules that are very incrementally being improved, but do a very specific set of things that countries could feasibly be able to do and agree to do, and that's why there's so much difference in the methodologies. So very commonly, they tend to use forest carbon accounting models rather than the sort of models we use, because you can do that much more specifically. So things like Werner Kurtz has got a forestry carbon accounting model, and in the UK we've got one, the FCAM model, that we use for doing the inventories, and we wouldn't use joules for it because it's just too different, doesn't work the same scale. Our forest carbon accounting model, you can put in species and management and it works in a completely different way. Yeah, it is. It's more, it's a bit more akin to the Houghton bookkeeping model if you're familiar with that, kind of. Some of them have carbon cycle feedback, so some of them have CO2. So Werner Kurtz's model can do CO2 fertilisation, the UK model can't. But yeah, they're more accounting models where you're putting in growth curves and things like that. I'm gonna actually pick into a bit of different methodology differences here. So, because I'm going to talk to you about different emissions estimates. And so I talk a little bit about what's in the different models, more from the science side now, so stepping away from the accounting and reporting, which is very specific set of rules that you could get countries to agree on, to what we're doing on the science side. And then Tom's going to drill more down into how you would actually do the modelling. So I'm not going to go into how you actually do the modelling, but more make you aware of differences between different models and different methods. Not all models. Sorry, ignore that overview. That was I'm not going to talk about the emissions gap. That's left over from my undergraduate lectures. We've already talked about the emissions gap, so that's ticked off. I did change my slides. They're not exactly what I've given my students. I've put in a lot more stuff that I wouldn't do with the students, but I obviously didn't check my overview slides, so apologies. I am going to talk to you about emissions from land activities and land-based mitigation potential. So this is a figure we put together for the IPCC that went in a summary for policymakers, and it looks at global greenhouse gas emissions from 1970 to 2010. Very nicely here, we've got the CO2 emissions from FOLU. We've got a bit of a change of acronym here. So in the UNFCCC and Kyoto Protocol, they tend to use LULUCF, land use, change and forestry. And the IPCC, and in some parts of the reporting, they talk about emissions from agriculture, forestry, and other land use. So FOLU, I think Alma mentioned yesterday. So those agriculture and then forestry and other land use used to be completely separate chapters in the IPCC Working Group 3, and they've been brought together into one chapter now to try and make it a bit more integrated. But here the emissions are separated out for the CO2 emissions just basically from land cover change. So that's in red here. The CO2 emissions from fossil fuel and industrial processes are that rather shockingly large bar in the orange, large strip in orange. Here we have methane emissions in pale blue, and as Alma said yesterday, the majority of the methane emissions are from agriculture and the land sector. And here we have N2O emissions, which also contain a lot of agricultural emissions, and then the F gases. Some key things to pick out here. Back in the day, in 1970, land cover change, CO2 emissions, were responsible for about 17% of emissions, and now it's about 11% of emissions. But I mean, they've not changed dramatically, but it's because the fossil fuel emissions have gone up so much. In fact, the CO2 emissions from land cover change is the only sector where emissions have gone down in the last decade compared to a previous decade. So breaking that down a little bit more and looking at emissions just from the land sector. This big red bar down the bottom, the dark red bar, is just the CO2 emissions essentially from land cover change. And that's the sort of thing that's been calculated by a lot of the models that you guys are probably familiar with. So the DGVMs, LPJ Guess and LPX and Joules and various others. And also the Houghton bookkeeping model, which is where this actual data is actually from, and this bar is from the Houghton bookkeeping model. So that's just CO2 emissions from land cover change. Then we've got emissions from Jane peat and fires, that's CO2, N2N and CH4. Rice enteric fermentation here, CH4 from cattle. Rice cultivation, methane here in yellow. Manure management, synthetic fertilisers, now we're moving into the N2O, manure on pasture, manure on soils, crop residues, cultivated organic soils, and this little bar at the top is burning savannas and crop residues. So you see how all the different greenhouse gas emissions from across the land sector, if you total those up, if you look at all the land sector as a whole, it's responsible for 24% of total emissions. So land cover change, CO2, is 11% of CO2 emissions. The whole land sector is 24% of all greenhouse gas emissions. And just to add that this land cover change emissions here, this is net land cover change. So this isn't deforestation, this is the net of deforestation, afforestation, and all those other activities. Yes, the main reason it's going down is because of reduction in deforestation rates, and that's I'm going to have some slides on that in a little bit. This is the carbon budget as produced by the Global Carbon Project. So this isn't the budget we talked about before, which is our emissions budget, our trillion tonnes. This is breaking down carbon sources and sinks and looking at the carbon budget. So we have emissions of fossil fuels that account for about 89% of CO2 emissions. And we've got emissions from deforestation accounting for 11% of emissions. And then about 45% of those emissions remain in the atmosphere. And just under a third goes into the oceans. And just under a third is taken up by land. And we don't have an exact handle on we know generally why the land is taking up carbon, but we don't have a very exact breakdown on it. But that's kind of largely to do with carbon dioxide fertilisation and with climate change already experienced. So this isn't afforestation or anything like that. This is just the response of the natural system to mostly environmental change. And that's quite a service the land is providing in being a sink for CO2. So when we come to looking at things from a more land ecosystem services perspective, that's quite an important service. So when we calculate that land sink, this sink here is often known as the residual sink, and that's because it's actually calculated as the residual from all the other terms. So we know we use a variety of data about energy and industrial data to work out what these emissions are in each country, and that's known with a relatively low uncertainty. You see it's 7.8 plus or minus 0.4. I'll go into how we calculate land emissions in a minute, the land use change emissions, but that's actually calculated with quite a high uncertainty. That's plus or minus 50% uncertainty in our land use change emissions. That's quite high. And that's part of what I'm going to talk to you about today, why that's so high. We can measure very accurately what the CO2, what the concentration in the atmosphere is, so that's known quite well from actual atmospheric measurements. The ocean uptake was largely based on models a few years back, but now there's increasing amounts of ocean measurements that number is now quite has quite a strong observational basis to it as well as models. And this has been the kind of what we don't know. And so it's calculated as the residual of all those other terms. So if you had emissions equaling sinks and you turn your equation around, then you calculate your residual sink from the difference between the fossil fuel and land emissions and the ocean and atmospheric sink. And then you come up with what your land sink is. So in the Global Carbon Project, we update the budget every year. And it's published in Earth System Science Dynamics, data discussions, usually led by Corinna Curry. And this is the ones from the latest paper. On the left here, Almut showed this figure very briefly yesterday and said I'd go into more detail, so I feel I should. Thank you, Almut, for that little. So over here we've got emissions from land use change, and then we've got the emissions from fossil fuels. And then we've got our known ocean sink in the dark blue, that atmospheric sink, or the atmospheric increase in the pale blue, and left over is what the land's taking up. And like I said, and here are those broken down individually. And like I said, the land sink is calculated as the residual from all of these other terms. And I suppose the thing to note from looking at this is here we've got from about 1850 to the 2000s is this rapid increase in fossil fuel emissions, and a bit of an increase and then a fall again in land emissions. The land use change here, you might notice that it's a dotted line, and then suddenly you've got a big peak and it becomes a solid line. It was quite difficult to decide what to use as our land use change emission sources, because in a minute I'm going to show you there's lots of models and they're all over the place and there's lots of different estimates. We chose for the Global Carbon Project to use the results from the Houghton bookkeeping model, but we have an issue that we need annual emissions estimates, and things like the fossil fuel and the atmospheric growth and the ocean sink, we can get hold of those numbers annually. But people like Ski Houghton and various other people who run models, they don't always run their models every year. And there isn't always the land use data to run them every year. So we switched to using a method. Guido van der Werf does a method where he uses satellites to look at fire. And then he has a particular methodology where he separates out deforestation, fire emissions from other emissions. And so we used, from the period that his data was available, we used them both to give us a bit more an idea about interannual variability, because Houghton's methods don't include climate and other things, so they can tend to be quite steady. So to give us a bit more an idea of interannual variability to reflect what's in the other methods, and also because we can update it annually. So we're just using the annual anomalies from Guido's satellite file stuff on top of the Houghton to give us that internal variability and give us the latest year. And there's a particular wiggle because 1998 was a very high fire year. So we break that down a little bit more, and here we have our land use change emissions up here. And this is showing you, again, if you can see, we've got that dotted line there, that's the Houghton changing into the solid line when we've got Houghton and van der Werf data together. And just to give you an idea, this is just the van der Werf fire data alone, and it comes out a little bit low because it's only looking at fire emissions, and there's lots of land use change that's not by fire. But for us, it's just using it to give us that interannual variability that we know happens because a lot of land clearing is by fire. Sadly, we're not chopping those forests and keeping the wood and using it for anything useful. It actually just gets burnt. And so it's possible to have more fires in drier years, so more land clearing happens in drier years. So there is this interannual variability that's not captured necessarily in the Houghton data because of the way countries report to the Food and Agricultural Organisation, the FAO, which is where Houghton's data comes from. All these green wiggly lines are all the dynamic global vegetation models that you guys are probably more familiar with, like, so Visit is in there, Jules, LPJ, GUESS, LPX, and other models make up all these little wiggly lines. So you can see there's quite a lot of uncertainty between the different methods. There's this range going on here, but Houghton is sitting somewhere more or less in the middle, and in the latest sort of emissions estimates. And here's the land sink. And the black line is the calculation we did with the GHG project of calculating it as the residual. But actually, the DGVMs are also able to calculate the land sink directly without doing this odd residual calculation. And so the green lines here are what the DGVMs get for calculating the land sink. Remember, this is the growth in sort of natural lands, not land use change. And actually, we were quite impressed year on year, still slightly amazed, that the residual we get from our budget calculation is quite similar to the residual that the models are getting directly. The yellow is the mean, the model mean for the residual, and the green lines are all the individual model results. And so you get your total land balance here, where the black is again the carbon, the what we get totally, the total net land sink, because the land is currently a sink overall when you consider land use change and you consider this uptake. The land is currently a net sink overall, and the black line again is our calculations, and the green are the models, with the yellow being the model mean. But interestingly, this year we've managed to look at another direct method of calculating the land uptake, and this is using atmospheric inversions. So the idea is you're measuring carbon dioxide in the atmosphere, at the same time you're measuring oxygen, and you can use the combination of the two and of other traces to determine what amount of CO2 is taken up by the ocean and what amount is taken up by the land, and to also look in different places to distribute that. And so when the atmospheric inversions separating out the ocean and the land, they actually also come up with quite a similar pattern to our residual budget. So it's just another line of evidence that's confirming that we can know what's going on, hopefully. So Mark showed this figure yesterday. So I decided I'd one-up him and not show that and show a slightly different figure, because mine's got a nice graphic. It's not more relevant to his talk than mine, but So this is a simulation by Julia Pongratz, who looked at land use change back through time and over history, and it's the expansion of cropland. So you're seeing the area of cropland expanding, and a deeper colour means more percentage of the grid cell is covered by cropland, so 100% covered by cropland, so a small percentage. And it's quite nice. If you start having a look, you'll see in Europe cropland expanding, and then any minute you should see the black cake hit, you see, and it contracted a bit, and now it's expanding again. And if you look to China, you see a similar thing with the fall of the Ming dynasty, a much smaller contraction, and then an increase in expansion again, and then by about now it's all just going nutty, and it's going to go crazy all over the place, and everywhere becomes quite covered in cropland. So it's a nice idea that you can see some of the drivers Mark talked about, some of the health drivers and political drivers, socioeconomic drivers that are going on with land use change, to bring us to what land use change. Sorry, that went up into the future, so that was where we're at with land use change today. So what's driving the CO2 emissions and land use change is mainly deforestation. And this figure here shows you the change in forest area by region from the FAO, so the Food and Agriculture Organization of the United Nations. Countries report, it's another reporting thing, but countries report to the FAO on area of cropland, on area of forest land, on different types of agricultural production, on wheat yields and maize yields, and all different kinds of things, and that's quite a valuable source of data. If any of you need data on some sort, how many of you use FAO data directly? Yeah, quite a few. So there's a website, FAO Stat, where you can go and get all this different kinds of data on the agriculture and forestry sector. They've also actually started doing emissions estimates for the first time, and I'm going to show you those in a minute in conjunction with some other estimates and talk to you about how they do that. But this, for the moment, is just showing you net loss of forest or net gain of forest over the 1990s and in the 2000s. Back to your question as to why the emissions are going down. So you can see that the net loss of forest in Brazil has gone down, the net loss of forest in Africa has gone down. There's also some countries where there's afforestation. Asia's changed from net forest loss to net forest gain, and there's been gains in forests in Europe. Just to prove my tree hugging credentials, this is sort of why I care. So when I was an undergraduate, I went and did field work out in Borneo, and this is a map of Borneo showing forest cover, and here it was in 1950. It wasn't quite 1985 when I did my field work. I'm not quite that old. It's a few years later than that, but it's near 85 and 2000, I have to admit. Here's where I did my field work, in this little dot here. And then this is the deforestation that's carried on. Here we are in 2010. The little area of forest where I work is actually protected now, but it's still becoming less and less surrounded by forest. And by 2020, it's predicted to have very little forest around it at all, relatively. So that's why I care about these things and these numbers, and why I'll look at them for endless hours, because I hope it will make some difference. These are some different estimates of the land use change emissions for the 1990s and for the 2000s. This was from a paper we put together, bringing together lots of different estimates. And we found the mean across the estimates at the time. So that was the Houghton model, but also lots of DGVMs and satellite. We found a mean of about 1.1 gigatons of CO2 in the 90s and 1.1 in the 2000s. And then the error we estimated, we just made an expert guess. There's no systematic assessment of error. We just really kind of went, well, we think it's probably about that. For the Global Carbon Project, we tried to do something a bit more systematic, where we looked at models that have been run with and without land use change, and with and without, with different land use data sets, and with and without different processes, to come up with a slightly more systematic assessment of uncertainty. And luckily, we found it to be about the same. And IPCC is different from that, just because we went for one standard deviation, and IPCC, they go for 2 standard deviations, and so that's why the uncertainty seems higher. The numbers are different because this is a mean across Houghton and what the DGVMs were at the time. These ones are based more directly on Houghton with the fire stuff, and Houghton runs a little bit higher emissions than the mean of the DGVMs was. And there it is in pictures. So I'm going to show you 2 or 3 of these horrendous spaghetti grams, where you've got lots and lots of different lines and different things going on. This was the one in the Houghton paper that those numbers were based on. And just to show you, Houghton is here in the red, and there you can see that in the periods of the 90s and the 2000s, particularly in the 90s, Houghton's running higher at the higher end of most of the other models and methods. Yeah, there's a lot of thought about that, and they're kind of being ironed out, and it's in the land use change data, and a lot of it's about the change in the way the past is being dealt with. And so it's different approaches to measuring pasture, and different bits of information come online. And so a lot of the newer historical reconstructions don't have such big peaks. There still are some changes that are really about sudden conversions of agricultural land, but those peaks aren't quite as high. I'm just trying to see. This still has the high 1950 peak, so it's more than some of the newer data sets coming online. So this is the one that was in the IPCC Working Group 1, and the black line's Houghton, and the other lines are lots of different models. Oops. And then this is the one we put in Working Group 3, a little bit different, because I was trying to make a different point here. I'm talking to a slightly different community, and also some new methods that come out. So I'm just going to run through these a little bit. We've still got Houghton here is the black line, and the blue lines are still different DGVMs. I just mentioned that FAO are doing their own emissions estimates, and these are the FAO emissions estimates here, and they're with and without peatlands. So the green line are including emissions from peat, and the dashed line is not including emissions from peat. Houghton doesn't include emissions from peat, and neither do any of the DGVMs at the moment. So that just gives you an idea of if those methods actually did include peat, the sort of perhaps increase there might be over what they have now. These bars, this relates to the Panatal paper. I don't know if any of you are familiar with Panatal. It was a science paper a while ago, and she used, it was a big team of people who brought together lots of data on emissions inventories. Are you on that? So they looked at inventories, actual sort of inventories in forests. Although in the tropics they use inventories in forests to really look at the residual sink term, but they still use the Houghton model to calculate deforestation emissions. And then in the European countries they used inventories, lots and lots of tree inventories to come up with the data. And so they found this reduction in the essentially deforestation emissions between the 90s and the 2000s. This is Boccini et al., and this is quite an interesting progress in data and estimates that's happened in the last few years. This is based on satellites. So you've got satellite land cover data. I'm sure lots of you are familiar with the Hansen and other products where they've looked at satellite-based land cover change. Then there's also new methodologies for measuring now tree biomass from airborne sensors. And so you can combine the satellite land cover change with the biomass, and to come up with land use change emissions. And that's what they did in the Boccini paper. That's also what they did in the Harris paper, and they did use a different land cover data set and also different biomass estimate, but also they used a different method. And actually most of the reason these two are different is not because of the different data, it's because of inclusion of different processes, which is something I'm going to get onto later. But the Boccini is a little bit more complete in terms of the different processes it considers. So that was the uncertainty at the global level. When you break it down to the regional level, then you've got even more differences between the models. So this is really just showing you the FAO stat is the green square, and the rest are all DGVM estimates. But there's some key things to pick out here. So in Asia, we're seeing a peaking for each of these is a different region. So we've got OECD, the reforming economies, Asia, Middle East and Africa, and Latin America. And each shows the emissions in the 70s, 80s, 90s, and the 2000s across a range of DGVM methods and FAO, and showing you the mean and the range. And so there's some key messages here. The decline in net emissions in Latin America due to a reduction in deforestation. A decline in net emissions in Asia, in part due to reduced deforestation in some places, but also due to a lot of afforestation in China and India. And in OECD, the picture's a bit mixed. You can see in that region, some models are actually finding a net source from land use change, and some are finding a net sink. And that's been to do with afforestation in different regions, but there's still a lot of difference amongst the models that needs to be packed out. I mentioned the PAN data, and this is a figure from PAN, and we adapted it slightly. It was going to go in the third assessment report, and I'm going to change it slightly, so the colouring is different from you'll see in the original paper, but the numbering is the same. The purple bars here, that's the forest carbon flux, as they called it, and what it essentially is it's the residual flux. It's the sink in natural forests that comes from inventory measurements. And then they've broken out the land use change flux into deforestation, gross deforestation fluxes, and tropical regrowth. So a lot of this is about shifting cultivation, where you burn, you do agriculture for a while, and then you let forests grow. So you've got forest regrowth as well as deforestation. And this was using the Houghton bookkeeping model, breaking out the deforestation flux from the regrowth flux. When you combine those, and you get the net land use flux. So here's your residual flux, and here's your land use fluxes for each country. And then, like I said, for the temperate and boreal countries, it was just all based on tree inventory data, so not separating out land use change and residual terrestrial flux, but that's the total net flux as measured kind of carbon stock change methods in all forests. So I talked a little bit about what's in some of the different methods, but I'll go into some more detail now on reasons for uncertainty and difference between the methods. So different data sources, I'm going to show you something on that first. Differences in estimating soil and biomass Carbon's quite a problem. In some countries we know there's carbon stock in forests and soils very well. In other countries we don't have much of a clue at all. Different processes that get included in the models, and even different methods of calculating the flux. So this was a study done with the ISAM model. It's a DGVM. I don't know if any of you are familiar with the ISAM model. It's an American model, but not very different from other DGVMs. It was run with 3 different land use change data sets. So that the HYDE data set, I'm sure many of you are very familiar with. So that's a data set put together by Kees Goldevik. I probably pronounced that awfully. Can you tell me how to... Goldevik. There we go. Tricky one to pronounce. And his data set is based largely on FAO cropland data. And it was what was used as the basis of the HERT data set. So I'm sure if you're not familiar with the HYDE data set, many of you will be familiar with the HERT data set, because that's what all the models had to use for writing for IPCC, the 5th assessment report. So you've got your HYDE data set here in blue. The RF refers to the Ramankuti and Foley data set, which is another one out there, also based on FAO methods. And when they're based on FAO from when FAO is available. FAO is only available from 1960. And then going back in time, you have to use all other kinds of methods, census information, assumptions about population and land use and, amount of cropland you need. So you have to use all kinds of different methods for hindcasting what your land cover change was. And HH is Houghton and Hackler, so it's essentially the data set Houghton put together, also based on FAO, but he tends to base it on FAO forest data. So he looks at forest area change and then makes assumptions about what that means in terms of agricultural change. So you lose forest, you've gained cropland, but not. And whereas HYDE data set is based on agricultural change and then assumptions about whether that increase in crop area came from forests or from grasslands. So there's quite a bit of difference, even though it's from FAO data, between the different data sets. And this is showing you land use change emissions that you get using the 3 different data sets when you run them with the same model, ISO model. And it also picks out some of the differences between, for example, deforested area, showing non-tropics and tropics. This is the HYDE data set going from the 1980s through to the 2000s for what you get for deforested area compared to what the Ramankuti and Foley data set shows you for area change, and ISAM shows you for area change. So you can see there's in here forest regrowth. So there's quite some difference between the different data sets, and there's nothing to say which one's right or wrong. Say that again. Because it's really, so the blue and the red one you'd expect to be quite close because they're both based on FAO cropland data. And the red one's different. It's just about interpretation of where you've got one of them you're basing on one area and forest change, and then you're trying to think what that means in terms of cropland, and the other ones you're doing the opposite. And so that's not to say that it's just an uncertainty really, and it's just what assumptions you make when you're doing that backcasting. But that's the only difference between them, is the amount of change in forest area or the amount of change in cropland area. And it's about this thing of my cropland's expanded. Did I cut down forest or grassland? That's a decision that the land use dataset developer has to make. And conversely, my forest has declined, has that turned into cropland or grassland, and those have very different emission profiles. And it is not to say if any is right or wrong. And also, that's going back to 1960. So it's also probably back to 1960. It's actually a little bit more about hindcasting. So it's probably not even about FAO data going back that far. So it'll be about using different data sources and assumptions about the amount of cropland or the amount of deforestation per population and given certain GDPs. With the same model, we, as well as looking at different the implications of different land use data sets, we also looked at running the model with and without nitrogen. So here you've got your 3 data sets again. They're not identified here, but the 3 different data sets. So the differences between the red lines and the blue lines are because of the 3 different data sets. But the big difference here is about running with and without a nitrogen cycle in the model. So when you run with a nitrogen cycle, what happens is your forest regrowth becomes nitrogen limited. So your emissions from land use change stay about the same, but your regrowth rate is slower, so your net emissions are higher. And so when we're breaking it down, when you look at the tropical emissions, weren't so different with and without nitrogen cycle because they're less nitrogen limited, but the temperate and boreal net emissions were very different with and without nitrogen because those are the forests that become nitrogen limited in the model. And so your net emissions end up higher. And so failing to account for nitrogen limitation, we reckon underestimated past global land use changes by 21 to 29% during the 20th century. Might be a bit on the high side or not, it's hard to tell, and more people are including nitrogen cycle in models, but it just shows that it could have a potentially very big impact. We ran it out into the future as well, using the RCP scenarios and using different climate scenarios from different models, and the underestimate going out into the future, so the 21st century could be as large as 90 to 150%. So those are quite high numbers, and really what needs is, yes, Alma. I was just going to say, it's the first model where this has been done, and other models might have stronger or less strong nitrogen. It's not clear, but the authors did look at lots of past forest data to validate the model in particular forests. Yeah, so that's what this is saying, is you include, yeah. Yeah. Yeah, well, I'm not sure if it's quite what you mean, but there's questions about how much the land sink will persist in the future and how much it will offset, and whether land then becomes limited in taking up so much of the carbon dioxide. Is that what you mean? We need to make the budget, make the budget, and you need a larger residual. Well, the only measurement constraint really is in terms of there's the inventories. If your inventories tell you that forests really aren't growing that much bigger, and at the moment the inventories are telling us as well that forests are growing faster, and mature forests are getting bigger. And then the inversions, which have a whole lot of uncertainties, but as we get more atmospheric measurements, the inversions are getting better. Yeah. Then I suppose we will know it because there's inventory measurements that are confirming this as well, and now atmospheric measurements. So we're getting to have a better handle based on observations, not just based on models and residual calculations of what's going on. And that was one of the big things in the PAM paper, as it said it confirmed that there is this big residual sink. Yeah, but a lot of stuff that's coming out, I mean, not just, you include the nitrogen cycle emissions are higher. If you include peatlands emissions are higher than we've been calculating in the past. So this looks a little bit at some of those different processes that aren't included in different models. So here's a few different models. The CO2 budget, this is Houghton, and then you've got Visit, ISAM, LPJL, LPJ Burn. Do they include deforestation, afforestation, and forest regrowth? Yes, they all do. That might seem an odd thing to say, but some of the methods that we looked at in the figure don't include regrowth. Some of the satellite methods don't include regrowth. Do they include wood harvest? That's quite variable, whether they look at what happens to harvested wood going into different pools that are rapid turnover or longer turnover. Shifting cultivation, whether they include croplands. Still quite a lot of the models don't include croplands. And we're just talking about CO2 emissions here. We're not talking about the other agricultural emissions. So these are still land use change. Peat fires. Big no. Actually, Houghton did put in some peat fire numbers, but only from 1998, which is another reason why the peat gets quite big, because they've got the fire numbers in there. Fire suppression, not many of the models have fire in there at all at this point in the version they use for this budget, although lots of them are putting fire in. Climate change and variability is an interesting one. So the models typically, they do have a change in climate and CO2 that they're run with. The Houghton bookkeeping model is a sort of accounting model where he looks at land use change and then uses growth and decay curves from the literature. So you say this area is change and this is my growth or decay curve, and so this is what I expect to happen to my carbon over time. So it's a counting budget, and so it doesn't take account of the transient changes in climate and CO2. It might be taking account of the fact that if you're using inventory data from today and that growth rate is already responding to CO2, in that way you might inherently include some CO2 fertilisation effect in your growth rate, but you're just using the same growth rate curve throughout the period. So it's not a transient change. So that's for the climate change variability in CO2 and nitrogen dynamics. At the time, this ISAM was the only one that had nitrogen dynamics in. Quite a few of the other models are putting them in or have them in already. That's one way about thinking what's in them or not. And then another issue is when you're talking about gross, Alma just mentioned the gross and net stuff, that becomes quite complicated because different people mean different things by gross and net. I don't even want to go into too much. But you have your gross sources you can think of as essentially your sort of deforestation, forest degradation, and your gross sinks is your regrowth. And you add those together and you come up with a net flux. There's also issues about fast fluxes and legacy fluxes that someone asked me about in the break. So the idea is you cut forest and you're going to have some immediate emissions. If you burn it, you're going to have a lot of immediate emissions, but then you're also going to have some slower decay over time as the whatever's fallen on the ground continues to decay, as soil carbon gets lost. You also have legacy regrowth fluxes, and that's what I was talking about when you plant your forest prior to 1990, and then you've got the legacy effects from your old management that's going on to the future. So you have all these different legacy flux. So all the sinks are kind of legacy because you plant it, it's not immediate, it takes a while, and you've got legacy sinks, and you've got these immediate, fast emissions, and then these slower decomposition and use of products, and then product decomposition, legacy emissions. So that's another way of thinking about what might or might not be included in different methods. And then also you've got deforestation and degradation, and you've got regrowth and reforestation, and other ways of thinking about splitting it up into different forest terms, which is more going into what we were talking about with the inventories, to come up with a net flux. That might be a net deforestation flux and a net degradation flux. You've got all these different issues, and when you look, not all the methods include all of these different fluxes. As I said, like satellites tend to be based on current measurements and not include the fluxes. And this also goes through the IPCC measurements. If you're using Tier 1, you're assuming all emissions are instantaneous. If you're using Tier 3 and you're using models, then you can kind of account for that historical flux and past land use. And so that all gets quite complicated, and Julia Pongratz has put a really good paper together where we really tried to look at these different flux components, and we tried to look at all the different methods out there and really work out what different method was using different fluxes and not. And this becomes quite a complicated picture, and you can read the paper, but I'll try and go through it with you just very simply. So the standard way for calculating the land use change flux in models, which you'll be no doubt doing later, is you run a model with land use change, and you run a model without land use change, and the difference between the two simulations gives you your land use flux. And that's what most models do. That's what all the DGVMs do. It's what's done with some of the Earth system models, although it kind of depends what mode they're running in and how they diagnose it slightly differently from IPCC. But really to be able to separate out the land use change flux, the only real way to do that is run with them without the land use change and the models. And there's three key processes that get accounted for in different ways. The first one of these is land use feedback, and that was what I was just saying about the impacts of environmental change, so the impacts of CO2 and climate variability. And so the GGVMs typically include that. The Houghton accounting method sort of implicitly includes it, but not transiently, so it's not accounting really for the change. It might be accounting for some of the effects, but not the changing effects over time. And the coupled models include it because it's all coupled, and when they've got their vegetation model in there, the changes are acting on the vegetation. The loss of additional sink capacity is quite an interesting one. So this is still talking about the climate and CO2 effects, and it's talking about the residual sink into the future. And what it's kind of saying is, I have a patch of forest here. In the future, this patch of forest is going to take up carbon because of CO2 fertilisation and climate change. However, if I cut down this forest now, then in the future it's not going to be able to take up that carbon dioxide that it would be able to do if it was still here now, if it's still a forest. And this is the loss of additional sink capacity. And that kind of gets implicitly included in some of the calculations and not others. And it can be quite significant. If you cut down a large area of tropical forest, in the future that could have, in your no land use simulation where that forest exists in the future, that could be taking up a lot of carbon. In your land use simulation, it's not there. That's not taking up any carbon. So that's quite a significant net emission you get. But it's not really a net emission because the forest isn't there. So does that make sense? There's a few nods in there. So it's kind of, a not real, it's a lost sink capacity. But in some of the ways you do calculation, then that can turn up as a land use flux. And the other issue is the legacy regrowth that we just talked about. And so depending on how you do your simulation, whether it's coupled or uncoupled, and the way you set it up, and the way you define land use, and therefore the methods you use, some of these things get included or not. And this is what this figure was all about. We tried to break it down and to see which the different models did. So here you've got your natural land, and here you've got your managed land. Here you've got a little bit of land that you cut down. And you have emissions that are, some of the emissions are immediate, instantaneous, that's the I, and some of them are legacy emissions that come a bit slower, that's the L. You've got fossil fuel burning that changes environmental conditions, and then you've also got land use change that changes environmental conditions. And those changed environmental conditions affect your natural land, and those change in environmental conditions due to fossil fuels and due to land use change, they affect your managed lands. And so you've got those effects. And so if you imagine it this way, if you imagine the directions going this way, you've got your natural land, you've got where it would be at without the environmental effects. And if you burnt it, those would be the emissions. And then you've got this little bit of extra biomass there because of the environmental effects. And so when you burn it, you've got some emissions again due to that little bit of extra biomass. And so those are what these things are about. It's the delta little extra bit of emissions from your CO2 fertilisation from fossil fuels and from your CO2 fertilisation from land, just to put it really simply. And then here, this is the potential land that you would have had if you hadn't cut it down. And that's also affected in your model when you're doing your no land use change runs by the environmental effects. And so you've got all these different components, and that's then tries to put it into a pattern here. So here we've got our managed land. Here we've got our potential potential vegetation that doesn't really exist in the future but would have done if you hadn't chopped it down. And here we've got our natural land. And instantaneous emissions and legacy emissions, just from from undisturbed environmental conditions undisturbed by human activities. So assuming no CO2 fertilization effect and climate change. And then you've got the little bit of extra you get from managed lands due to the instant and legacy due to fossil fuels, and legacy due to the CO2 from past land use change. So you've got your little extra bits of emissions and also sink due to the environmental changes. It's very complicated. You can look at it in detail at length. I'm a co-author on the paper. I have to read it every time again before I present it to remind myself. It's very complicated, but Julia's a really great thinker, and it's a really good way of thinking about breaking it down. And when you get into doing models, it's good to know. And this is your additional sink, lost additional sink capacity, and this is your residual sink. And so what we find when we look across different methods, we've got the Earth system models, we've got the inventory bookkeeping model, and we've got DGVMs down here. This is where our majority of our DGVMs sit in this one. You can see that some of them include different components of fluxes and some of them don't. And therefore, when we're looking at my horrible spaghetti render diagram of everybody's different fluxes, this is you see why they're different. And actually, just those differences in methodologies can make as much difference as differences due to really different data sets and other things going on. And this is just to show you some of the differences between using with and without the land feedback effect. So this is Julia run her model, and different people run different models with and without the land feedback going on. Give you an idea of the sort of difference that makes. So I got a little bit of only a short time left now to talk through mitigation. The emissions bit was the main thing I wanted to go through, and I wanted to make you aware of what's out there, and then Tom's going to talk in more detail. We're running short of time. What time do I have to leave, Tom? 5 minutes. So I could either run through mitigation or I could just take questions. It's up to you. Yeah, well, I had a few questions during, so that made it a bit slow. So do you want to have questions on the emissions, or do you want me to talk to you a bit about mitigation? Okay, mitigation. Okay, so I'll run through this a little bit quickly. You can always email me questions. I'd be really happy to ask. Alma will answer the questions for me. Yeah, I mean, I hope that's all right. I prefer to have questions during, which some of you have done anyway, so that's good. Okay, so this is the IPCC results. There's just a quick couple of things I want to pick out here. So it's just to turn it back around and bring it into perspective. So mitigation in different sectors. Transport, buildings, and here we are, net AFOLO here in predictably in green. We've got baseline emissions, business as usual, what would happen going out into the future in the 2030s, 50s, and by 2100. This is to limit it to 450 ppm, so this is your 2 degrees. These are the results from all the integrated assessment models that were run that had a 2 degrees, and kept to 2 degrees. With carbon capture and storage. Now, if you remember from my last lecture, we talked about negative emissions. The only thing that gives you negative emissions is afforestation or bioenergy with carbon capture and storage technology, and that being because the bioenergy supposedly releases as much as CO2 as it takes up in regrowth, and then if you use technology to take out that CO2 and bury it under the land, then you've got negative emissions. And you see there's quite a, well, it's hard to see actually, there's quite a heavy reliance on bioenergy with carbon capture and storage. That's what's going on here in the electricity sector. So the bioenergy negative emissions are kind of accounted for in the electricity sector. And here's your negative emissions and carbon capture and storage. Here's your negative emissions from afforestation. If you think that we won't have carbon capture and storage technology ready, or that even if we had the technology ready, you don't trust the fact that it will actually all be stored and stayed in the ground, then you have to do even more really dramatic things in the land sector to still achieve 2 degrees, and that is massive, massive afforestation. As I'm sure you can imagine, that would have a lot of implications for food production. So I won't go into those are just two different assessments of what mitigation potential was. Someone asked about top-down, bottom-up. The IPCC was quite a top-down assessment of IAM's integrated assessment models that are being forced to get to 2 degrees. You want to get 2 degrees, you're throwing everything out you can. We also did a bottom-up assessment of if you actually say, I've got this much land, what do I do with it, where do I get to? And actually the mitigation potential on the land is not so different from looking top-down or bottom-up. And here's some of the bottom-up results. So you can look at what you can do in the food supply chain. And so, for example, switching to a no-ruminant diet or switching to a no-meat diet at all gets you different amounts of CO2 savings. So the greenhouse gas reduction potential, purely plant-based diet is 7.8%. Compared to, and this is what Harvard Medical School say a healthy diet should be, including some meat, is 4.3 gigatons. Did I say percent? Gigatons of CO2 emissions. And again, this one's looking at available land. So you've got a certain crop area and grazing area, and you make different assumptions, like you change your diet, so you don't need so much land for producing feed for animals, or you change your yield, or you reduce wastes. Then what happens? What would be the change in your carbon sink on farmland? What would happen if you afforested all that spare land? Or what would happen if you implemented bioenergy on that spare land? And there's quite a range here because there's quite a difference in the range across bioenergy technologies. And again, then that's how we come up with your different mitigation potentials based on different scenarios. I won't go into this one because this is about the bioenergy potential, and I recommend looking at the special report on renewable energy if you're interested in bioenergy. It's quite a complicated issue, but what I will talk about just briefly is the difference between is consideration of the technical potential as opposed to the actual implementation potential. So there's a high technical potential for bioenergy, but what might actually get implemented is likely to be a lot lower, and I really recommend looking at the special report for that. But then I want to make a kind of final point, which is that even if so land is important, right? We said it's 11%, we said it could be really important, but even if you replaced all of the land, this is a little back of the envelope calculation we did for IPCC third assessment report, there's even if you replace all the land that you've deforested with forest, your carbon concentration at the end of the century would only be 40 to 70 ppm lower. So the land can do a lot. I think it's really important, but it's limited. Complete deforestation would give you a higher concentration of 130 to 290 ppm. So stopping deforestation has more of an impact than even if you afforested all the land. So there are limitations. So land can do a lot, but there are limitations. This I just thought was quite a nice thing that looked at the contribution of policy to past mitigation. Someone kind of asked a question about this. So policies that have happened in the past and how much they've contributed to emissions reduction. And the Montreal Protocol, CFCs are actually greenhouse gases, so that's contributed a lot. We've got hydropower, nuclear power, and here's Brazil forest preservation and Indian afforestation. And then they did a similar thing looking into the future for mitigation potential. And here we've got Brazil forest preservation, Brazil ethanol, but quite a big potential contribution from avoided deforestation in Brazil. So my key messages on mitigation are there are many options already exist. I need to go, yeah. And many co-benefits, but trade-offs and barriers and issues which Mark went through and Anna will go through in more detail. So that's it. I'm going to stop there.